Hello dear students, welcome back. I'm Chetan Rajoria from APES Engineering College, Ghaziabad. I'm covering up unit number 1 of the subject Fundamentals of Mechanical Engineering. The subject code is BME 101 or BME 201. So in this video lecture series, in this lecture, I'm going to cover up the stress strain diagram. This is the 13th lecture of the video lecture series, and we will discuss the concept of the variation of stress with strain, how the stress varies with strain for different kind of materials. We will discuss the variation of stress with strain for mild steel, which is a type of low carbon steel. Then we will discuss same curve for some other ductile materials also. And then we will discuss the same curve for brittle materials. So let's start. So dear students, in the last lecture, we already discussed the fundamentals of stresses and strain. We discussed about what is stress, what is strain, and different kind of modulus of elasticities. And we also discussed what is Poisson's ratio. Now let's see how the variation of stress takes place with the variation in strain. Suppose we have a specimen, a bar-shaped specimen, rod-shaped specimen like this, and we are conducting a tensile test on a UTM, that is Universal Testing Machine. Okay, this is the specially designed specimen, and we are gradually increasing this tensile force F from 0 to maximum. We are increasing this force gradually, and we are observing the developed stress and the developed strain in this specimen. So always remember that stress is a dependent quantity and strain is the independent quantity. Because of the strain developed in the material, the stresses are developed. So we take strain on the x-axis and stress on the y-axis. So as we increase the amount of force, this tensile force on this specially designed bar-shaped specimen, initially the stress is proportional to strain. So we obtain a straight line. This line will be, this line will be much closer to the y-axis. This will be a perfect straight line. I'm sorry if you're observing this like a curve because I'm drawing freehand, but remember, it is a perfect straight line. You can use a scale for drawing this line. Okay, so it is closer to the y-axis because elongations are very small in the beginning stages, but stresses are developed drastically faster. It indicates the material is offering some resistance against the elongation. That's why the stress induced is much larger as comparative to the change in strain, or you can say change in length of the workpiece. After that, there will be a limit or a point will be there. This point is called limit of proportionality. Limit of proportionality. It is the point up to which the stress is proportional to strain. The Hooke's law is obeyed up to this point only. This point is called limit of proportionality. After that, we can observe the curvature starts. Then there will be a point B, which is called limit of elasticity. Limit of elasticity. It is the point up to which the material shows the property of elasticity and it loses this property after this point B. If we remove this force F after up to point B, the material will regain its shape, initial shape and size. It will spring back to its initial shape and size if the externally applied load is removed. And this will happen up to point B only. After point B, we will observe a certain amount of permanent deformation in the material. So That spring type of behavior is observed up to point B only. That's why this is called the limit of elasticity. Then the curvature continues and suddenly we observe a drop in the value of stress. The point from which the drop in stress starts is called upper yield point, and the point up to which the stress drops is called the lower yield point. C, D are upper and lower yield points. This point is a very significant point on the stress strain diagram. After this point, we observe a large and permanent deformation which takes place in the material. Before this point, the elongations are very less, and the rate of increase of the stress was faster. But after these points, the yield points, the elongation takes place with a much faster rate. We can observe a permanent deformation which is clearly visible through our naked eyes. That phenomena takes place after the yield point. Therefore, it is very important, especially for forging or permanent deformations. So these points are upper and lower yield points. After point D, we observe a zigzag type of behavior in this stress strain diagram. Very, you can say, slightly zigzag type of behavior will be observed, and then the material regains its shape. The stress increases, but which are comparatively lower rate, and the elongation increases with a much faster rate. Then there will be a point where the stress will be maximum. This point is called ultimate tensile strength or maximum tensile stress. This point is E. Ultimate tensile stress. It is also called maximum tensile strength. After point E, the stress strain curve drops once again. It is the maxima of the whole curve, point E. After point E, the neck formation takes place. If we observe the material after point E, we can clearly observe the neck formation, which takes place like this. There will be a drastic reduction or sudden reduction in the cross-section area, somewhere where the cross-section is the weakest. At that location, we can observe the neck formation, and it happens after point E. And finally, the material breaks in a cup and cone type of fracture. On one part, we can observe a cone type of arrangement, or you can say cone type of shape, and on the other part, we can observe a cup type of shape. So material breaks in cup and cone type of fracture at approximately 45 degrees with this axis. So this point is the fracture point. So material breaks at point F, fracture point. The portion between D and E is called strain hardening. This portion. Strain hardening. This portion up to point B is called elastic zone. And after point B, okay, elastic zone was up to point B, and after point B up to point F, it can be considered as plastic zone. The area under the stress strain diagram gives you the value of toughness of the material. Higher the value of this area under stress strain diagram, higher will be the toughness of the material. So it indicates the amount of energy absorbed by the material before its fracture. That is toughness. So these are the significant points on the stress strain diagram for mild steel. So basically, first of all, you should know what is mild steel. Mild steel is basically a low carbon steel having 0.1 to 0.3% carbon. And we have conducted a tensile test on a specimen of mild steel. So such kind of behavior is observed between stress and strain. These are the few salient points on the stress strain diagram of mild steel. Now, what happens if we conduct the same test for some other ductile materials? So very much similar kind of diagrams are obtained for other ductile materials. First of all, we will observe the Hooke's law part, that is, the stress is proportional to strain, and we will observe uh, very small elongation and very large increase in stress in the beginning stages because the material opposes any kind of external applied force. It resists any elongation. So similar O to A curve is exactly identical. Then the curvature starts, but it continues like this. The value of stress doesn't drop like this, C to D. It takes place in case of low carbon steels like mild steel, but such kind of behavior is not observed in case of other ductile materials. So it is a smooth curve. The stress continues to be increased, but with a lower rate, and the elongation starts with a much faster rate after a certain point, and then it drops like this. So we can observe A point, B point, means limit of proportionality, limit of elasticity. Then there will be a point called yield point. There is no upper or lower yield point. Only a single point will be observed here, which is called yield point. Then there will be point E. There is no point D here, okay? So there is a point E, which is the maxima of the whole curve. This is called ultimate tensile strength of the material or maximum tensile stress of the material. Then the neck formation takes place as usual and we get the fracture point. So almost all the points are same except that instead of two yield points, upper and lower one, we get only one yield point. Now how to identify where is the yield point? Because it's a smooth curve. There is no sudden drop. In this diagram, we were observing a clear location of the yield points C and D, especially point D is the yield point. But in this case, how to locate where is the yield point? For this, we take the maximum elongation, or you can say maximum value of strain. Suppose this is the value of maximum strain, mark it as 100%. Mark 0.2% of the whole strain here. Only 0.2% of the whole strain. And draw a parallel line parallel to this line, the Hooke's law line. This line will pass through the yield point. In this way, we can locate the exact position of the yield point. Okay, so this is the stress strain diagram for other ductile materials. So while explaining this diagram, you will once again point out these salient points A, B, and C, that is limit of proportionality, limit of elasticity, yield point, ultimate tensile strength, and the fracture point. All the things are same except the shape of this curve. So you will also mention here the elastic zone, the plastic zone, the strain hardening part, as well as the neck formation. Next one is the stress strain diagram for brittle material. The main thing in case of brittle material is that there is negligible amount of elongation. The material suddenly breaks after the elastic zone, or you can say the any brittle material shows certain amount, very small amount of deformations. Those elongations or deformations are within the elastic zones only, and they are even further very, very small. But after that elastic location, elastic limits, the material abruptly breaks. It breaks into two parts suddenly and without any elongation or yielding. No yielding is observed in case of brittle materials. So if we draw a stress strain diagram for brittle materials, so we get a straight line once again, which is closer to the y-axis. It is a perfect straight line. And then a little bit curvature can be drawn here, which indicates that yield point is about to come, and without actual yielding, a sudden fracture takes place like this, point F. Before that, it was proportional limit and elastic limit and so on. Only you can mark A and B points, limit of proportionality and elasticity, but after that, you can directly show the location of fracture point. Yielding means elongation. So generally, large elongations are not observed in case of brittle materials. So it is actually the difference between a ductile and the brittle material. The ductile materials are those which shows large permanent deformations before fracture. We can convert any ductile material into thin wires. That is the property of ductile material. But in case of brittle materials, they show a sudden permanent deform fracture. Sudden fracture is observed. Okay, abrupt fracture is observed in case of brittle materials. So the width of the whole curve is very, very thin. Okay, this part is a very small part as comparative to the previous two curves. Okay, the strain is very large in case of ductile, but it is very less in case of brittle materials. So a flat failure is observed. There is no cup and cone type of failure. Two pieces are separated suddenly and abruptly. Flat failure, okay, like this, without any particular shape or cup and cone. No such kind of shapes are observed. So this is all about the stress strain diagram for mild steel. For other ductile materials, maybe aluminum or copper or any other alloy. And this is for brittle materials. The slope of this part of the curve, where the curve is actually a straight line, the slope of this part indicates the modulus of elasticity, that is Young's modulus. So we can also compare the Young's modulus of two materials by putting the curve, the stress strain curve for both the materials on a single plot, X and Y. So in this way, this curve is very, very helpful for studying the behavior of elasticities of different kinds of materials. So thank you so much for this lecture.